Scanning electron microscopy (SEM) gave us nice details on the morphology of certain materials. In some cases we want to see more details that cannot be seen with SEM. In that case we must use transmission electron microscopy (TEM). Transmission electron microscopy, known as TEM, is a microscopy technique to create an image of a sample. A TEM microscope uses a beam of electrons generated by an electron gun. These electrons are focused via various lenses on the sample. An image is then formed from the interaction of electrons with the sample, once the beam is transmitted through it. To create such an image, the specimen must be ultra-thin, typically in the order of 100 nanometer or less, and placed on a grid. The transmitted electrons are detected by a detector, creating an image. This image is further magnified so it can be viewed by the operator on, for instance, a monitor. TEM microscopes have a significantly higher resolution than light microscope because they work with the much smaller wavelengths of electrons. This allows us to visualize even single atoms, obviously way smaller than can be achieved by a light microscope. Since silicon is an interesting electrode material for lithium-ion batteries, we have chosen this as an example. Silicon expands significantly once lithium is inserted, which may lead to cracking of the silicon as a result of the building up of internal stresses. Therefore, small particles are chosen to avoid these strong stresses. TEM is an excellent method to analyze small particles, and even the atoms of a silicon particle can be seen with this method. It also allows us to see a difference between the bulk and surface. This is particularly important to analyze the actual surface structure and eventually composition. Another way to avoid cracking is to deposit a layer on top of the silicon. This layer then serves as a kind of elastic layer that expands together with the silicon and forces the silicon back to the original shape once lithium is removed. A possible layer for that was suggested to be a titanium dioxide layer. Here a TEM image is shown for a 150 nanometer silicon particle with a 4 nanometer thick titanium oxide layer. TEM confirmed uniform coating of this TiO2 with controlled thickness. Similar as in scanning electron microscopy, SEM, incoming electrons may have enough energy to promote an electron from a lower energy level to a higher energy level. Once an electron has been removed, it is possible that other electrons in higher orbitals fall back in the created electron gap under irradiation of X-rays. These X-rays thus can be measured with which is called EDS or EDX, energy dispersive X-ray spectroscopy. It is important to realize that this radiation is element specific. This means that a recorded X-ray spectrum is a fingerprint of the elements present in the sample. Even the intensities of the X-rays gives an indication of the concentrations of the elements present in the sample. This typically happens in the subsurface area. EDS coupled to TEM has been used to image nanosilicon particles coated with TiO2. Signals of titanium near the surface clearly demonstrate a silicon TiO2 core shell structure. Operando TEM was also used to study the expansion of the silicon nanoparticles during lithium insertion. Silicon nanoparticles were deposited on a TEM grid. A lithium metallic electrode coated with a solid electrolyte was slowly brought in contact with the silicon nanoparticles. A voltage was applied to force lithium to move from the lithium electrode through the solid electrolyte to the silicon nanoparticles. A real-time analysis was recorded. But one of the concerns for a solid-state cell is the contact between electrolyte and electrode. So when using silicon nanoparticles, it would be useful to study the point contact, where the solid electrolyte, especially since silicon may lose its contact with the electrolyte due to its volume changes. To achieve the objectives, an in situ sample holder is utilized to create a nanoscale battery, where the piezo motor moves the solid electrolyte to the silicon nanoparticles, thus creating contact. And silicon is lithiated by applying a negative bias and positive to delithiate it. On the left-hand side, we see the TEM cross-section with the lithium-coated electrode on the bottom and several silicon nanoparticles on the top. These nanoparticles were deposited on a copper grid. Here we can follow real-time the insertion of lithium in the silicon nanoparticles by applying a voltage. The silicon nanoparticles are expanding till contact is maintained. After breaking contact, several lithium particles starts to shrink and other slowly starts to expand. This is due to the slowly moving of the lithium from one particle to the other. We will show you this movie again. This process has been mimicked at the right-hand side. In summary, TEM gives us information on morphology and the surface of matter. EDS, coupled to TEM, provides elemental analysis and the distribution, particularly on the surface of particles, and operando TEM can be used to monitor insertion behavior of certain electrode materials.